Good morning, STEM ninth graders. We're going to talk a little bit about how to complete the PWC portion and maybe some of the math portion as well for your Catapult launch. Now I have here the chart that you'll see on your PWC Catapult analysis. You got the displacement, the time, the initial velocity, final velocity, and acceleration. I have an X dimension and a Y dimension. We're launching this payload in two dimensions. We launch it up and over, basically. So some amount of that is upward when we launch it at some initial velocity at an angle. Some of it is upward, and we call that initial velocity VYI. It's an initial velocity in the upward dimension. And then we launch some of it to the right, VXI. If we only launch it straight up, it's not going to go left or right. It's just going to go up and come back down because its VX would be 0. So we're going to talk about how to think about each of those dimensions one at a time, instead of trying to imagine what's going on at two dimensions at once. So there were two measured variables we asked you to measure, or I asked you to measure. We asked you to measure the distance that it goes. That distance is actually the displacement in the left and right dimension, in the X dimension. So if you launched from here and you wound up over here, that dx is your distance of your launch. That is your displacement in the left-right dimension. So let's say you launched it and it was 5 meters. Okay, I'm going with round numbers. Your numbers should be more precise than that. Try to get to 2 decimal places. Okay, so let's say we launched at 5 meters. And you were also asked to measure the time of that launch. The time of that launch, let's say, was 2 seconds. Now, displacement, as you'll notice, has a dx and a dy component. Time, there is no tx and ty, because however much time it spent in the air going up and down, it also spent the same amount of time going left to right. So that one we can put in both dimensions as 2 seconds. That'll be the only variable that is the same in both dimensions, at least not by coincidence. Anyways, so we have 2 seconds in the air and 5 meters. All of you should have measured your distance of launch and your time of launch. So now we're going to draw your attention to the acceleration portion of this. If you draw a force diagram of your payload while it is in the air, the only force acting on it, assuming no wind resistance, is the force due to gravity. If the force due to gravity is the only thing acting on something, it will accelerate downward at the acceleration due to gravity, or sometimes just called g, which on planet Earth is 9.8 meters per second squared. So now we know that that acceleration is in the downward dimension. So we're going to go ahead, I should probably make that a negative to be consistent. In the y dimension, it's going to accelerate downward at 9.8 meters per second squared. As long as you're on planet Earth, that's the constant you use. Later, we'll look at what happens if you have a different acceleration due to gravity because you're on a different planet. But for now, we're on planet Earth, so 9.8. Now, also looking at your force diagram, you'll see there are no forces acting left or right, which means the net force left and right is 0. And if the net force is 0, the object will not accelerate left or right. And so our x acceleration is 0 meters per second squared. Okay, so now that you have that, you have a distance and a time. We're going to look a little bit more at these types of things. Let's look at the x dimension first. So I drew up the bulldozer, which is an equation you encountered with a different name or no name in math class. And in my class, I call it the bulldozer, so I don't have to say all the variables all at once. Now, I drew the bulldozer, or wrote the bulldozer for both the x dimension and the y dimension. So if we go through our chart and we plug in, we have dx equals vxit plus 1/2 at squared. But notice in the x dimension, ax is 0. 1/2 times 0 times t squared is 0. And 0 added to anything is itself. So that term essentially goes away. And in the x dimension, the bulldozer simplifies to dx equals vxi times t. Now, if we're solving for vxi, we're going to take that equation and we're going to divide both sides by time. dx over time equals vxi t divided by time. Time cancels here, and we find that dx divided by t equals vxi. Some of you more observant folks might notice that that is actually just the speed equation. Velocity, in this case, these are both vectors, so you got to be careful, but velocity and speed are quite similar, except one doesn't have a direction. Just distance divided by time. So in this case, my particular numbers, vxi would equal 5 divided by 2 meters per second. So I would get 2.5 meters per second. So I go up here, my vxi is 2.5 meters per second. Now I also might notice that the acceleration is 0. Remember, acceleration is a measurement of how much velocity changes over time. 0 change means it does not change. And so our vxf is just 2.5 meters per second as well, because it started at 2.5 meters per second. There was no force acting left or right to slow it down in its rightward motion, however much it got launched to the right, the vxi. And so the vxf, right before it hits the ground, is also going to be 2.5 meters per second. So that does it for the x dimension. That'll get you all the numbers you need. Now the y dimension, there's one big trick and one big thing you need to notice. We're assuming that your catapult launches from the ground, goes up to some maximum height, and then falls back down to the ground. If it does that, remember, displacement is just like location. It started at the ground, it wound up at the ground. The change in location was ultimately 0 meters. Yes, it went up and came back down. It went some distance, but its location in the universe is now 0 meters above where it started. With that trick, our equation now, we can cancel out dy. And if we do that, we have 0, because that's what dy equals vyit plus 1/2 ay t squared. Now I'm going to subtract 1/2 ay t squared from both sides, and it'll go away. So we now have negative 1/2 ay t squared equals vyi times t. Now we're looking for vyi, so we're going to divide both sides by t. That cancels that off, and we have vyi equals t squared over t. T squared over t just equals t, because t is t times t, divided by t just leaves 1 t left. So we now have negative 1/2 ay t. For my numbers, I can plug that in, and I can say negative 1/2 times negative 9.8 times 2 seconds equals, coincidentally, 9.8. Now, yours isn't going to be that clean, and notice this is 9.8 meters per second, not meters per second per second. So I'm going to go up here and I'm going to say, okay, it was launched upward at 9.8 meters per second. I regret using 2 seconds because you all are going to get confused, because 9.8 meters per second looks a little too similar to 9.8 meters per second. But that's because of the time in the air. Okay? So now, once I realize that, I can now think about what's going on in 2 dimensions kind of together, or what's going on in the launch. So let's think about this. 9.8 meters per second, and it's negative. That means it's accelerating downward at 9.8 meters per second. It's losing 9.8 meters per second of speed or velocity per second. Now, if we think of this as like a mirror image, we come over here to our diagram. This is the ascent, and this is the descent. It was accelerating at the same rate in both dimensions, and it went up some displacement and fell down the same displacement in the other dimension. So actually, the time of ascent equals the time of descent. So time of ascent equals time of descent. And if you add those up, time of ascent plus time of descent would equal total time. In our case, that's 2 seconds. And if TA is the same as TD, then TA equals 1 second and TD equals 1 second. Together they make 2. They're half of the total time. Okay? So thinking about that and thinking about if it accelerated upward, its velocity upward was 9.8 meters per second, accelerated downward. It lost that 9.8 at its peak, where its Vy right here at peak equals 0, because it turned back around and came down. And after another second of falling, it picked up 9.8 meters per second, or for 1 second. And so it's now going to hit the ground going downward at negative 9.8 meters per second. Okay? So we know now this symmetry that it mentions in the document, right? It was going up, it came back down the same distance, so that whatever velocity was launched upward with, it comes down at the opposite to that. Okay. Now there's one more thing that you have to do for your math, which is to figure out what was that maximum height. Okay? The easiest way to do that is to use the bulldozer again and say dy equals vyit plus 1/2 ayt squared. Now we have to use this trick that at the very peak, its velocity was 0. Or if we just analyze the descent, it's like it got dropped from its maximum height and fell down. So Vyi, we're going to say, is 0. If you just analyze the descent, Vyi equals 0. That cancels off this term. So dy, or the displacement downward from its peak, equals 1/2 times negative 9.8 times the time of descent, which we said was 1 second. So, and we square that, but 1 squared is 1. So now we find that 1/2 times negative 9.8 times 1 equals negative 4.9 meters. So we can say that it fell 4.9 meters from its maximum height. And so its maximum height was just 4.9 meters. Okay? So you guys are going to do the same thing for your own data. You should have gotten your own dx and your own t. Okay? You should have 2 decimal places, meaning like 5.13 and 2.19, but I was keeping the math simple for myself. So your numbers are going to be different there, but you guys are going to follow the same process. Think about the left-right dimension and the fact that it's not accelerating. And then think about the up-down dimension, which is almost just like our rocket launch. And there it is accelerating up and down. So in each case, you get one of those terms to cancel, and it simplifies the math considerably for you. So please use that in your analysis, and that should get you going. And good luck to you. Have a good morning.